Hello, and thank you for inviting me here. During this talk, I will mention things like interpolation, like we heard in Fernando's talk, and things like Hardy spaces, like we heard in Alexei's or Adolf's talk. But I wanted to start with a very instructive example that sounds very, very simple, but that showcases what is going on. Please. So suppose P is a polynomial, and suppose Z1 up to Zn are zeros of that polynomial, and that's all. This Z1, Zn could be real, complex, could be pairwise distinct, or could be counted with their multiplicities, or P could have other zeros. But let's just start with something very simple. Then the thing is, the following dichotomy holds. Either P has to grow really fast, or it has to be identically zero. This sounds like one of the uniqueness theorems that we typically have in analysis, and this could be proved by any high school student. But what is instructive is how they would prove it. So here's how we go. Because, say, Z1 is a zero for P, by the polynomial remainder theorem, or little Bézout theorem, you can factor out Z minus Z1 out of it. Then you repeat it over and have a product. Then, by some combinatorics, you turn a product into a sum. And finally, you say either Q0 is identically zero, or P grows at least as fast as Z to the n does, and you have it. The problem is when you think about things more general, like entire functions or something like that, there are much more factors in there, and the combinatorics could get more involved. So what I propose is, even for this simple case, thinking about something different. Thinking about P as a sum of monomials right away. So you have a representation of P like that. And then using something that high school students don't know, the maximum principle. In a circle large enough, P and Z to the m has the same number of zeros. Z to the m has m zeros. P has at least n zeros. So n is less than equal than m, and you have it. Avoiding combinatorics and avoiding something that would include, say, Weierstrass theorem for entire functions with tempering infinite products and things like that. So let's go to the next slide and see that if we not only know that there are n zeros, but something more, then you can tell something more about the polynomial, please. Vieta's formulas. So if you know that certain numbers are its zeros, then it implies certain facts about the coefficients of the polynomial. So not only you know that it will grow really fast, but you know the highest order term in its asymptotics and thinks about lower order terms. So I wonder if there's something like that for analytic functions. So it seems like a very basic thing. Vieta's theorem for polynomials we know very well, but is there something like that, some phenomenon like that that holds for analytic functions? And next I go with these simple examples even further, talking about a function g of z equals sine pi z. Now sine pi z has infinitely many zeros, at least natural numbers are its zeros. Now I write g of z as the sum of exponentials. It's just I write it in a very elaborate way, these and these together. So g as an integral now, and it's integral with the following discrete measure. So actually a sum of exponentials. Now see what happens if you loop this measure on a circle, you get identically zero. Something like that. I brought with me the imaginary axis, that's the zero, that's I pi, that's negative I pi. I loop it over, 0 stays 0. Is this a circle? They both go to -1, so they cancel each other. If you think about not sine pi z, but sine something other z, and do the same thing, then the resulting function will be 0 at natural numbers only and only if you have identically 0 here. So you have to loop every time, and they should cancel each other. So an effect like that holds for general trigonometric polynomials too. This condition, g at n equals 0 and natural numbers, is equivalent to the following. You write g as an integral of exponentials with respect to a discrete measure, then you loop it over. Instead of I omega k, you think of e to the I omega k, so you took it on a circle, and this condition is equivalent to the following condition on the coefficients of ck. So this is a condition on the coefficients of the trigonometric polynomial for it to be 0 at natural numbers. Just like for Vieta's theorem, it relates zeros and coefficients. This does the same, and it's a necessary and sufficient condition. So with this much preparation, we are ready to go to general analytic functions. If you could please go to the next slide. Yeah, so a very basic theorem that lies in the crossroads of many things about interpolation, analytic continuation, numeric approximation, and so on, is a theorem of Fritz-Carlson that says if G is holomorphic in the closed right half plane, then the following holds. For if G is 0 at natural numbers, then necessarily the following dichotomy holds. Either it's identically 0, or it has to grow really fast on the imaginary axis. And if you don't like complex analysis at all, growing really fast would correspond to having higher order frequencies on the real line. So it says if there are no higher order frequencies, if it doesn't change too fast, then knowing its values at natural numbers is enough to restore it. In particular, if it's 0 there, then it would be identically 0. In order not to be so, it has to have high frequencies. And that's what Carlson's theorem says. And it is an if-then theorem. Now, I wanted to formulate if and only if type of theorem, a necessary and sufficient condition that complements Carlson's theorem. So here's how it goes. Suppose G is holomorphic in the open right half plane. It could have been an angle or something. It should include the numbers 1, 2, 3, 4, and so on. And for 0, I don't even request that it includes it. I want the limit at 0 to be 0. So suppose it's analytic in the open right half plane. I include the condition of it being exponential because that's where the condition lies. Then the following if and only if condition holds. G is 0 at natural numbers only and only if G could be represented as an integral of exponentials over a measure. Remember, that was what I proposed for polynomials, to start with a representation rather than to start carving out factors when you have zeros. So we have a representation here. We have exponentials, we have a complex measure, and what is important, it's an integral over C. So it's a bit more involved than the usual Laplace transforms that you would have. It's not an integral over IR, it's an integral over C. And then the condition is, if you loop it over, so consider the mapping that associates to a set E, the set E to the E, so it goes inside a disk, then this new measure, mu, will be a measure in a very large circle. Now, you take a measure in a very large circle and you sweep it to the boundary of the circle by the sweeping theorem, or called balayage theorem, which means sweeping in French, but because the French were the first to work with that, so you consider its balayage and consider this boundary values that you would get from this measure. So a necessary and sufficient condition is that this function is in the complex valued Hardy space H1, and it's 0 at 0. So if you think about it, if you think about a function on a disk, how would you say it's in H1? You say you take its Laurent expansion, and the coefficients with negative indices equal 0. So C minus 10 equals 0 exactly corresponds to G at 10 being equal to 0. And we have here G at 0 is 0, so I put additionally that H at 0 is 0. So this average integral over the rim of a circle is 0. So this is a necessary and sufficient condition for a function to be 0 at all these points. Now, once we have a representation, and if we want to think about Carson's theorem, if we want to imply a large growth, remember what happens with polynomials. We had a representation of a polynomial in terms of a sum of monomials, and then we use the maximum principle. So in a disk large enough, a polynomial has as many zeros as its main term. So here, corresponding maximum principle should be somewhere to imply Carson's theorem. So what would be the maximum principle? What would you think about for maximum principle for the Hardy space? So if we go to the next slide, it's our good old friend Riesz brothers boundary uniqueness theorem, that it says if f is in H1, then it could be either identically 0, or it cannot vanish even on a set of a positive measure. So you can think about it as a maximum principle, because if it's 0 on a set of positive measure on the boundary, then it's 0 everywhere inside. So the Riesz boundary uniqueness theorem that doesn't allow you a situation like that, a function being here and missing an arc in its values, so a supporter function being there. If you go through the theorem, it will imply that the measure, its support, is bounded away from negative pi I and pi I, which will in turn imply that its indicator at pi half and negative pi half cannot grow fast enough. So this maximum principle is what you use to infer Carlson's theorem from this necessary and sufficient description of the things that we had. Next, I would like to have some kind of historic context of what this theorem is and where it comes from. Carlson's theorem proved by Fritz Carlson in 1914 in a thesis published in Uppsala, and I couldn't find it anywhere on the internet. Everyone cites it, but there's not it. And I would be very interested in knowing what it is, because it has many applications. So I wonder what Carlson's original motivation was. I suspect it had to do with analytic continuation, but I really wanted to know. And what is interesting, I found the paper of Hardy of 1920, who reproves the theorem of Carlson. And in the remark, he says that he got it independently from Carson, in fact, earlier than him, and he wrote it to Mittag-Leffler, and Mittag-Leffler confirmed it. So somehow it could be that this theorem is proved independently by Carson and Hardy. And there's even a variant of it when you assume the function is 0 not only at natural numbers but at all integers. And this variant, they claim, was originally obtained by Wigert. That's about the original proofs and the original results. However, this theorem could be proved in alternative ways. So Japanese scientists Yoshino, Suwa were using planar summation formula, a formula that restores the values of a function, of an analytic function by its values at certain points. And that formula was derived from Mitsuo Morimoto's integral representation. And Mitsuo Morimoto's integral representation is what I have copied in the theorem above. If you could go 2 slides back, back, not forward, back. Yes, that's Morimoto's representation. So you see it's over a complex plane C, not a line, and it is unbounded. So this is the thing that allows you to transfer it to something very, very straightforward. If you could please go forward 2 slides. Yes. And there are proofs of Carlson's theorem by that representation, except they don't do this additional step and going all the way to the Hardy space. And this representation, there are other representations too. If you think about the space of analytic functions and duality, so one of these duality representations was used by Avanesian and Gay to recover Carlson's theorem again. Now, I wanted to say a few words about how central this Carlson's theorem is. And if you go forward 1 slide, please. Yes. Many mathematicians have worked on it, trying to generalize it in this way or other. So I tried to list everyone I could find on trying to substitute the condition of the function being 0 at natural numbers to it being 0 at a general sequence going to infinity. So the general conditions they have is that the density is 1. But also there's this more abstract result of Malyavin and Rubel saying when G will vanish on a sequence, on an arbitrary sequence of positive numbers going to infinity by relating to its growth on the imaginary axis to a growth of a different function. So this is one way of generalization, the way that you think not of natural numbers, but of any sequence. And this way of generalization is important when you think about completeness of exponentials, when you think about what power should there be so that a system of exponentials is complete. Also, there were other types of generalizations. For example, this is Ralph Boash and Trembinska. They think about not the function being 0 at integers, but being summable at integers. So sum of Fn in its absolute values is convergent. And I would very much like to advertise these surveys of Braichev and Sherstyukov, and also a book of Bulat Habibulin. They review all these types of results with more general things like you don't get zeros to be on an array, but like 2 rays, and want to talk about it, something like that. And also what you could have is what if instead of this condition of growth at infinity being the integrators being larger than n, you nail it to indicator being n, but at the same time it's very close to n. What will this infer? So neutral results, they belong to Kazmin and Valeron. What happens when the growth is substituted with a bit stronger or weaker one? So things like that. So I hope this would somehow convince you that Carlson's theorem, its generalizations have been area of continuous interest of mathematicians coming from different areas of mathematics. And the reason why they come from different areas of mathematics is that Carson's theorem has many applications. If you could go to the next slide, please. Yes. One more thing about generalization to higher dimensions. So we have generalizations for holomorphic functions, not analytic functions, for higher dimensions. And from a point of view, you can even consider Nevanlin's theorem as a generalization of Carlson's theorem. And also Berling-Malyavin's multiplier theorems have been considered as an analog of Carson's uniqueness theorem. If you go to the next slide, please. Here, I wanted to talk about the applications that I could find over. So one basic thing about this is restoring Newton series uniquely. That is, suppose you have a function and you know its values at integers. If you have a polynomial and you know its values at some points, you have this Lagrange interpolation formula. If these points are the integers, they call it the Newton interpolation formula, because that's how Newton originally thought about it. If you make not end values, but a sequence of values, that you would get a massive formula that would somehow correspond to restoring the function. So this massive formula would restore a function only and only if the function doesn't tremble too fast. And when will it tremble too fast? That's described by Carlson's theorem. So Newton's series and its restoring in a unique way, and more general interpolation problems that caught the interest of Jonathan Pila in 2005. Actually, the reason I was interested in that is that it is used in analytic continuation. So paper by Alexander Vagharshakyan about analytic continuation got me interested in this, and I hope this will have applications there. So that's the direction I'm thinking now. But it also has all kinds of things, like consider Ramanujan's master theorem. You know, this over-involved formulas that Ramanujan was getting and impressed Hardy so much. And when you have the factor 1 over pi there, the reason pi gets there is because of Carlson's theorem. And you could have some versions of Mergelian approximation theorem when they do it not with polynomials, but with Lacunary polynomials, so that they only allow some powers to be used. And in there, Carson's theorem is like explicitly mentioned, for example, in this result. And as I said, it has to do with completeness of exponentials. And for example, like I pick a recent paper by about completeness of exponentials, like Olewski and Ulanovsky. You know, Olewski has like a research group on completeness of exponentials. They have very good results and now developing to higher dimensions. I took nearly a random paper of theirs, Olewski, Ulanovsky, 2011. And they have a factor in their formula 1 over 2 pi. And then I want to understand how this factor comes into place. It's because of Carson's theorem. So it's that interrelated, everything from completeness of exponentials to Lacunary approximation theorems, to interpolation theorems, and all the way to Ramanujan's theorem. So it lies as the cornerstone of analysis. If you go to a next slide, oh, this is more of like a last slide. So I just wanted to say that when I tried to research more on Fritz Carlson, I ran into his biography. And it says that there are two important results related to him. One is this Carlson uniqueness theorem, and the other is the following inequality that is called Carlson's inequality. And the historical anecdote is that he was thinking that his inequality was like an independent fact of a property, and it turns out that Hardy proved that this inequality, in fact, could be implied from Schwarz inequality. So another theorem of Carlson's, now Carson uniqueness theorem, seems like it could be implied from this brother Rees uniqueness theorem, which also allows, to avoid sets of measures zero. And if you think in spectral terms, Carlson says you have to be over pi on the imaginary axis for the measure, and Rees' theorem says whatever you take, you just loop it over to the interval, and then you cannot even avoid a set of positive measure. So that's it for my presentation. Thank you.
Thank you very much for the very interesting and intriguing talk. We have some time for questions, so please. Yeah.
Maybe you mentioned Hardy and Carlson sort of so Hardy was after, but on the other hand, Hardy sent a letter to Mittag Leffler.
Yes.
Before or after Carlson?
Yes. So what I'm saying is I copy from the article of Jeffrey Hardy of 1920. It says on a theorem of Carson and Wigert, and right on the first page, after the formulation, there's the note on it. And the note says the following. So this is all according to Hardy. So this remark should be made. So this is, there are some things that are absolute truth, but there are some things that are according to Hardy. Shouldn't be very far, but he says that he obtained that result without knowing about the results that Carson got, and he sent that result to Mittag Leffler. And then he learned about Carlson's result that was published. So he approached Mittag Leffler to ask for his permission to publish that result too in his proof. And he says that Mittag Leffler allowed him to do so. So this is the whole story. I think it's all these stories, all these small things are so interesting because they show these people as like real people and humans beyond the theorem. So I'm kind of fascinated by stories like that.
Further questions, please.
Yes.
Do you know any integral generalizations of this inequality?
Oh yes, I once ran into something like that. Yes, yes. You have to Google Carlson's inequality rather than Carlson's uniqueness theorem, and it brings things like that. Yes.
And probably this provides some embedding theorems.
Yes, it's exactly where these things are used in providing, embedding theorems. Exactly. Yes, yes, that's right. Yes, yes. Not that like everything is known, but people have been working in that direction. Yes.
Thank you.
Any further questions, please? If no, then let's thank the speaker once again.